In this lesson, we are going to focus on area under a curve and arc length when we're dealing with polar coordinates. So just like before, when we found an estimate of an area under a curve, we made rectangles and then we added those areas of those rectangles up. Now we're going to do something similar here with polar curves. We're going to use what's called a sector, and we're going to find the area of all these different sectors and then add them up. Now an area of a sector is when you look at a circle and you're looking at one wedge or one piece of pie in that circle, that's called a sector. So right here, this here is a sector. It's like a piece of pie of the circle. And so we need to remember the formula for the area of a sector. It's 1/2 theta r squared, and theta needs to be in radians for this formula. So if you're dealing with degrees, you have to make sure you translate that into radians first. So what we're going to do is we're going to use this formula and we're going to break up our area into multiple sectors, and we're going to add up all of those areas together. Now, just like before, as we make those sectors smaller and smaller, and we add in more and more, our area is going to get more accurate. So if we take the limit as capital N goes to infinity from 1 to capital N of all of these sectors, then we are going to get this integral here, where r is our formula for the radius of whatever our polar curve is. And then we are going to evaluate that from angle alpha to angle beta. In this case, if we just look at it generically, if we start here, that would be alpha. And then if we swing open and we want to look at the curve up to this point, find that area under the curve up to this point, that would be angle beta. So the integration limits are going to be angles. Here's our official theorem. Let's look at our first example. This says, let's find the area of a polar region. We want to find the area of one petal of this rose here. So we want to find the area of this one petal here. Now all the areas will be the same, but I'm going to use this petal right here because it's the first one. Okay, so I know that when we graph this, it's going to come out and then it's going to stop at 0 again, and then it's going to come out and make another petal, and then another petal, and then another petal. Every time it hits that center and it swings back around, that's when we're starting and stopping a new petal. So I'm going to set my equation here, my r, equal to 0, and I'm going to find those angles where that starts and stops. So I know that I want to find this angle, this theta, so that sine of 2 theta is equal to 0. Now this is going to be some multiple of pi if this whole thing is equal to 0, right? Sine is 0 when we're at a multiple of pi. So to find theta, I'm going to take and divide both sides by 2. And so I'm going to have some multiple of pi divided by 2. That's going to be all my thetas. And when I think about that on the interval from 0 to 2 pi, these are all the angles that I'm going to get that satisfy this. So our first petal is going to go from 0 to pi over 2, then from pi over 2 to pi. Then we have a third petal from pi to 3 pi over 2, and then we have a fourth petal from 3 pi over 2 to 2 pi. So I'm just going to pick one of these. It doesn't matter which one because they're all going to have the same area. I could go from 3 pi over 2 to 2 pi, and I'm going to get the same answer as if I went from pi over 2 to pi. But I'm going to pick this one here because 0 is going to make the arithmetic a little bit easier. So when I set this up, I'm going to go from 0 to pi over 2. So I'm going to use this petal here to find my area. And here's our value of r. R is 3 sine 2 theta. And our formula, if you recall, for finding the area, we're going to go from some angle to a second angle, then we're going to take 1/2 r squared d theta. So here's 1/2. Here's my r squared. My r is 3 sine 2 theta. And then here's my d theta. Now I'm going to square this. So I have 1/2 times, and then when I square everything that's on the inside here, I am going to get 9 sine squared 2 theta d theta. So if I combine that, that gives me 9/2 sine squared 2 theta d theta. I'm going to make a substitution, and I'm going to say let u be 2 theta. So du is 2 d theta, which means d theta is going to be 1/2 du. I'm going to do a substitution, and I'm going to get this. Now, because I did a substitution, I also have to remember to change my limits. So when theta is 0, my u is going to be 0. And when my theta is pi over 2, my u is going to be pi. So I changed my limits from 0 to pi because I made a substitution. Then using the tables, and I could use a trig substitution here as well, but using the tables, I am going to find that sine squared u, when integrated, is 1/2 u minus 1/4 sine 2u. And I got to remember to carry that 9/4 out here. And I'm going to evaluate this from 0 to pi. And when I do that, I get that my area of one petal is 9/8 pi. Now, if I asked you for all 4 petals, by symmetry, each petal has the same area, you could literally just multiply that by 4. So the previous example involved finding the area inside one curve. And now we're going to go through an example of how to find the area between 2 polar curves. So we have 2 polar curves here. We have r is equal to 2 plus 2 sine theta. That is this dark blue curve right here. And then we have the circle, r is equal to 6 sine theta. So that's this orange colored curve here. Now, in order to figure out how to sweep open what our limits of integration are going to be, we need to figure out what this angle is, and then figure out what this angle is so that we can figure out how to sweep open between the two to find our integration limits. So to find these intersection points, we're going to set the two equations equal to each other. And so I have 2 plus 2 sine theta is equal to 6 sine theta. When I subtract 2 sine theta from both sides, I have 2 is equal to 4 sine theta. I'm going to divide both sides by 2. And so I'm going to get 1/2 is equal to sine theta. So I need to figure out the angle in which I would get 1/2 when I plug it in for sine. And when I think about the unit circle, I get that theta is pi over 6 and 5 pi over 6. So this angle right here is pi over 6. And this angle right here is 5 pi over 6. So we want to sweep open from here to here. Now, to find the area between them, we're just going to subtract. We're going to find the area for the first curve and subtract the area from the second curve. We specifically need to use this curve first, since this is the one above. Okay? So I need to make sure that here's my r squared for this curve here. And then I subtract r squared for this curve. So that's r squared for the first curve, r squared for the second curve, and then I subtract them. Don't forget, we have this 1/2 in front based on our sector, area of a sector formula. We have 1/2, and then we integrate r squared d theta. And then we're doing this, we said, from pi over 6 to 5 pi over 6. And we got to remember, of course, our d theta. Okay, so the first thing I'm going to do is I'm going to square each of these and try to clean it up the best that I can. When I square 6 sine theta, I get 36 sine squared. And when I square this, remembering I have a minus on the outside here, so I'm squaring all of this, that's all inside these brackets here. So when I square this, I get 4 plus 8 sine theta plus 4 sine squared theta. Now, when I combine like terms, let's see, I have a 36 sine squared theta. And because of this minus, I'm really subtracting a 4 sine theta. So that gives me a 32 sine squared theta. And because of this 1/2 out front, that gives me a 16 sine squared theta. I have a minus 4 for my constant, and when I take it by 1/2, I get a -2. And then there isn't really anything I can combine with this other than dividing by 2 because of this 1/2 out here. So I have a minus 8 sine theta divided by 2. That gives me a minus 4 sine theta. So all I did up to this point is just clean up this big mess. Now, when I integrate each of these, I take -2 and integrate, I get -2 theta. When I integrate -4 sine theta, I get -4 cosine theta. And using your tables, I get this here. I get 16 times 1/2 theta minus 1/4 sine 2 theta. And then I have to evaluate that from pi over 6 to 5 pi over 6. And when I do that, I get a total of 4 pi. So what that tells me is that between these two curves, when I sweep open this angle from pi over 6 to 5 pi over 6, this shaded area here is 4 pi. The last topic that we're going to talk about in this lesson is arc length of polar curves. Now, before we jump into the actual formula and work through an example, there is an important point that I want to make here because it's really going to affect your answer in the long run. So think about a circle, and if I trace the circumference of a circle twice, that arc length is going to double because I'm going around the circle twice. So it's really, really important when we're calculating our arc length, because we're dealing with things that could possibly repeat, we want to make sure that we're only tracing through the shape once. If we start sweeping through more angles than we need to be, then it's going to add on to our arc length and give us an inaccurate answer. So here's an example of what I mean so that you can visualize it. So this here represents a circle in polar form. So we have 6 sine theta. When I graph that, you can see the circle here. But if I were to go find the arc length of this, and I wanted to find the arc length of the whole circle, what I would intuitively want to do is set up my integral from 0 to 2 pi, because I'm thinking it's a circle. That's the way, it runs through a full cycle from 0 to 2 pi. However, some of those points are not unique. They restart to repeat, as we've seen before. So if you look at my window here, although intuitively I might want to set up my integral from 0 to 2 pi, notice that my angle only sweeps open from 0 to pi here, and I get that full circle. So if I actually put 2 pi here, it would draw the circle twice on top of each other. So watch what happens. If I put in here 2 pi, whoops, and then I draw the graph again, you don't see it because you only see that one circle, but it actually went through and wrapped around and drew and traced through that circle a second time. So if I go from 0 to 2 pi, I'm actually going to double my arc length. So you want to make sure that you're using your limits so that you're only getting through one full complete cycle and that you're not going through more than once. So now let's actually walk through an example of finding arc length with polar curves. Here's our formula. We're going to go from angle alpha to angle beta, and then we're going to take the square root of r squared plus the derivative of r squared times d theta. So in this particular example, it's asking us to find the arc length of the cardioid 2 plus 2 cosine theta. Now, there may be times where the problem might state, find the arc length from this angle to this angle, in which case you're safe because you know exactly what your limits should be. But if you want to find the arc length of the entire polar curve, then that's when you have to be careful and make sure that you are not going and setting your limit so that you're going through and tracing it more than once, so that it's going to cause you to get an inaccurate answer. So if you're asked to find the arc length of the entire curve, I would definitely somehow, in some way, double check to make sure you're not going through the cycle more than once. So you can either do it by hand and pluck some points to see where it starts to repeat, if any, or you can graph it and play around with the window to see what your angles should be. So if we go in and we actually graph this, so I have 2 plus 2 cosine theta, I'm going to start by going from a minimum of 0 to a maximum of pi for my angle. And so when I hit the graph, notice that I don't have that full curve. So I'm going to go through and set my window and try a different angle. And I'll try, say, let's do 3 pi over 2. So when I do that, I'm still not getting the full shape. So when I go to hit window, this time I'm going to try 2 pi. Now my intuition tells me this is going to do it. Hit enter and graph. So there's my full cardioid. Now, like I showed you before, sometimes it will trace through twice through the angles of 0 to 2 pi, which is why it's really important that you double check to make sure. So in this particular case, we are going to go from 0 to 2 pi. And so I'm going to do the square root. I'm going to use r squared. Since r is 2 plus 2 cosine theta, I'm going to have 2 plus 2 cosine theta here and square it, plus, and then I'm going to have the derivative of r squared. The derivative of this is negative 2 sine theta, and I'm going to square that. And then, of course, that's all under the square root. So now when I square 2 plus 2 cosine theta, and I square negative 2 sine theta, I'm going to get this big mess underneath the square root. Now, I'm going to clean this up a little bit by factoring out a 4 from all of these. When I factor a 4 from all of these, I get a 1 plus 2 cosine theta, and then what I'm left with here is cosine squared plus sine squared, which is 1. And then, of course, I can combine these 1's inside the parentheses and make that 2 plus 2 cosine theta under the square root, and this 4 can come out as a 2. So that's this 2 right here. And then inside the square root, imagine that you're going to factor the 2 out, and you're left with 1 plus cosine theta, because we're going to use this here in just a second. So now what we're going to have to do is we're going to use an identity to make a substitution here so that we can integrate this a little bit easier. So we're going to use one of our double angle formulas. So we have cosine of 2x is equal to 2 cosine squared x minus 1. I'm going to add 1 to both sides. And so I have cosine of 2x plus 1 is equal to 2 cosine squared theta. So whatever this angle is here, it's going to be double this one. So I'm going to rewrite it so that this is theta and this is theta over 2. So now I can say that cosine of theta plus 1 is equal to 2 cosine squared of theta over 2. So I'm replacing this 1 plus cosine theta with 2 cosine squared theta over 2. So this 2 and this 2 multiply to give me 4, and then can come out as another 2, which makes this a 4 outside. Then what's left underneath the square root is cosine squared theta over 2, and when I take the square root of that, I'm left with just cosine of theta over 2. Now, I want to make sure that these values are going to be positive because we're talking about length here, and I don't want any negative values to screw up our answer. So I'm going to make sure that we're using absolute values here. So to make sure that we handle this properly, if we look at, I drew a sketch of the picture right here. Here's the sketch of the picture. So if I just look at the top half, when I go from 0 to pi, it's going to be the same thing as the bottom half because it's symmetric. So instead of going from 0 to pi, I'm going to go from 0 to pi and double it so that we're not worried about those negative numbers. So I'm going to take 8 times the integral of 0 to pi, and I'm going to have the integral of cosine of theta over 2 d theta. When I integrate this, I'm going to get 2 sine of theta over 2. This 2 is because of this 2 right here. Remember, we got to do chain rule in reverse. So that's where this 2 is coming from here. And then when I evaluate this from 0 to pi, if I plug in pi here, I get sine of pi over 2, which is 1. And I get 1 times this 2 here, which is 2, and then 2 times 8, which is 16. Then when I evaluate it at 0, this whole thing disappears because I get sine of 0 is 0. So I'm not going to have some other term that I have to subtract here. So my final answer is going to be 16 for the arc length of this cardioid.